So now we're going to expand our thinking about molecules in 3 dimensions to ringed structures. So right now, this big model that I have here is cyclohexane. And it turns out that cyclohexane can go through multiple conformations. So you can see with this big model, it's kind of moving around and the different substituents are switching into different positions. And what we're going to do in this class is learn how to think about those conformations in 2 dimensions, so in the dimensions of writing it on a board. To start things out, though, we kind of have to think about how we've been representing things. And every single time so far in this class that we've drawn a cyclic structure, it's just been drawn planar. So all of these bonds of the cyclohexane that are drawn here and that are on page 1 of your chair structures online packet, all of these bonds are just normal. They're not wedged. They're not dashed. So that would imply that they're all planar. And if they're all planar, then we can look at this by a Newman projection and kind of see why it might not be the most stabilizing thing for a 6-membered ring to be entirely planar. So that's what we're going to do on your page 1. You have this same structure and the face here showing how you're going to look at this chair or this cyclohexane ring. So go ahead and pause the video for a minute and draw a Newman projection of what you would see looking at this angle, and then unpause and we'll do it together. But what that Newman projection looks like should explain what we can add to this line here. If cyclohexane was planar, it would be destabilized by a blank. So you've now drawn your Newman projection, and what you should have drawn is this CH2 of the ring is near my chin, so that's going to be coming down here, and we'll just write ring because it's the carbons of the ring. So this was the ring. And I have one H going up that direction, the other one's going that direction, so they're going to be like this. So that is this front carbon here. The back carbon is connected by this bond. And we know that this wedge is in the same plane as this wedge, so these hydrogens are going to be eclipsing one another, and we could say the same thing about these dash bonds. And further, this carbon of the cyclohexane that we've labeled ring here is in the same plane as this carbon of the ring, so we know that those CH2s that are part of that rings are also going to be eclipsing one another. So if cyclohexane was planar, we can now see that it would be a pretty destabilized molecule. We have a fully eclipsed structure that would lead to torsional strain and steric strain of those groups being too close to each other. So we can say that it would be destabilized by fully eclipsing interactions. Fully eclipsing interactions. So we can use those same Newman projections that we used for acyclic structures to explain why cyclohexane doesn't take on this planar state, but instead takes on something that we call a chair structure. And on that first page of the online note packet, it says cyclohexane is not planar, it is a chair, just like I wrote here. And on the right side, I kind of show a chair, and then I show the cyclohexane kind of on top of that chair, and you can kind of see how they would name it a chair. But with it, if we look at this model, this here is kind of the back of the chair, this is like the seat of the chair, and this is kind of how where the feet would go. But why would this chair structure be a more stable structure than the planar cyclohexane? And I have the chair structure drawn here, and I've drawn in those hydrogens, and now we're going to look at it at this angle. So let's look at it with this model. So here's our model that is just like this. And what we're doing is this eyeball here is looking down this bond angle here, and that's this bond right here that my hand is on. So let me bring that around to the camera, and you can see what that would look like. So, and what it looks like is it's staggered, right? Here's that bond, here's the ring, here's the ring. We have this hydrogen that is staggered from this hydrogen and this ring part. We have this hydrogen that is staggered from this hydrogen and this hydrogen. So everything is staggered in this in this chair structure, and obviously it helps to have the models yourself. They're available for purchase, and also you can come to my office and use them if you're interested. But when we look down this angle, what we see is that, again, my chin would be near that hydrogen there. So we're going to put that hydrogen going down. This hydrogen's off to the right. And then the ring is over here. On the back side, this one's going down. So we have the ring over there. We have a hydrogen up. That's that hydrogen. And this hydrogen there. So we see that when the cyclohexane is in the chair structure, all of those different groups are staggered from one another. And that actually is what we would put in the next blank. Chair structures move substituents into the staggered conformation. So that's what you're going to want to put on that page 1. Chair structure moves substituents into a staggered conformation. So we can write here that this is a staggered conformation of substituents. So that substituents is obviously going to be a lot more stable than if they were all eclipsed like this, which explains why cyclohexane rings take on this chair structure. One other thing that I want to talk about real quick is when we draw chair structures, we don't draw wedges or dashed arrows. Well, why is that? That's because what we're trying to do here is draw the molecule in perspective. So this is kind of the closest thing that I can kind of show with how these two are related. But essentially, this part of the chair right here is here, and we don't draw the wedges or dashes because they're not really coming out or going up. It would be really complicated to draw wedges and dashes on a chair structure because we're trying to draw it kind of in perspective. So we are going to continue to work on drawing these chair structures, especially in the next video. And it's going to take practice, and it's something that you'll get better at the more that you do it. So, all right, so we'll see you again soon.